All right. Does that work? All right. So welcome to the, what, 30-ish, 31st-ish episode of the OKC Python. Today, I'm going to basically cover a lot of information that O'Reilly, an author for O'Reilly, has provided in this functional Python primer. Like the URL's there. There's a QR code you can actually scan and look it up. But we try and do a lot of these techniques in our organization, and the pizza's here. So, like, don't mind me if you want to like get some food. O'Reilly, as in the book publisher. Yeah, they have. Right. Not the auto parts store, no. The other guys. Aww. Womp womp. It's always fun and exciting at the Python Talk for pizza. Like, so the things that we're going to cover, this is super awesome. I wish I could make this bigger. Like, for some reason, I don't get the slides on my side. So why do we want to do functional programming? Like we can make some adjustments to how we deal with flow control. There's the different models of callables, lazy evaluation, which is something that you can sort of emulate like Haskell with, and then higher order functions, which is a big part of functional programming in general. So one of the biggest concepts of functional programming is that everything you can do with data, you can do with a function. You can pass functions to other functions. Higher order functions are functions that operate on functions that operate on functions. Oh, by the way, they will be drilling, so like that's at some point. Yeah, that too, but so in Python, functions are first class. They are objects. Recursion typically is used as a loop construct in functional programming. We'll get into a lot of these things here in a little bit. But one of the more important things is the worries about what is to be computed instead of how. It's imperative programming is more of what you're used to. In fact, no, that's a couple slides down, but we'll get more into that as well. And like obviously we want to utilize higher order functions. So the why. Like these seem pretty easy to understand as far as concepts. Like you want your code to be easy to read, easy to write, composable. Like you want to be able to take pieces, put them together, make bigger programs, make better programs. It also helps remove a large class of difficult to debug errors in program logic because you don't have side effects, or you try to not have side effects. So, like, is Python a functional programming language? Like, no, it really isn't. Like, you can do it, but it's mostly OOP and imperative. So, avoiding flow control. Usually a block of code, you've got some outside loops, like a for or a while, assignment of state variables, modification of the data structures inside the loop, and then branch statements, your ifs, tries, all those fun things. That's cool. Getting notifications pop up over here and they're not showing up over there, which is perfect. So these are the things that you normally do in programs, and they're easy to reason about when you are thinking of things in this way. But with side effects, or you get side effects that come with state variables and mutable data structures. So, you often model the concepts from the physical world with containers, like your classes. Those are containers for data, but they're mutable. Like every time you run something on them, they change. That's the point. They're there to keep state. So instead, we'll focus on not constructing the data collection, but describing what the data collection consists of. And instead of, we'll think of, here's some data, what do I need to do with it, rather than the mechanism of constructing it. And hopefully we'll get to a more direct reasoning rather than, having huge chunks of code that describe more hows than whats. So one obvious way of focusing more on the what than the how is simply to refactor code, and you put all your data construction in a more isolated place, like another function or method. This makes this construction more testable as well. And this is one thing that we really try and do a lot of in our organization. But one thing I disagree with on this right-hand side is the get initial state. I would probably pass in the initial state, because that way it's easier to test, even more so than this. Using comprehensions is often a way to both make code more compact and to shift our focus from that how to the what. So these comprehensions use the same keywords as loops and conditionals, but you invert the order to focus on the data rather than the procedure. Changing the form in this way can make a difference in how you reason about the code. Obviously, this one on the right is shorter than the one on the left, and it's sort of a little Englishy, but it's very clear what you're doing with the data in each condition, or clearer to me than the one on the left. But you also avoid needing to think about or debug what's the state of the collection at this point of the loop. You don't have to worry about, hey, have I added this to the loop, to the collection yet? Because that happens in your comprehension. And Python has generators, set comprehensions, and dict comprehensions, and you can nest them to an arbitrary depth. Don't do that. Like, you can add lots of complexity very quickly. It's much better to turn them into more methods. We'll probably see some of that in a bit. Generators. It's the same syntax as list comprehensions. Sometimes you need parentheses syntactically in some contexts, but they're lazy. You save memory, you defer your computation until necessary. And you can tell it's sort of easier to read. Instead of looping and making a data structure and repeatedly calling append, you can make, dicts and sets all at once. Just say, here, this is what I want my set to be. Or here is what I want my dict to be. These are the things I want in it. So recursion. Recursion is very popular in functional programming. Python doesn't support it well. There is a stack depth limit of 1,000. Unless you change it, but that probably means you're doing something wrong. There's not a lot of reason in Python to use this approach. And in fact, in this case, just having a loop that updated total would be more readable, use a lot less stack, and wouldn't explode if your list was 1,000 long, 1,001 long. Yeah. other languages that more heavily depend on recursion have this fancy thing called tail call elimination, which, let's see, that's not a real good recursion example. This one on the right, this factorial R, basically what it does is fakes that last call to factorial and resets the stack like it's going into that same function again, but moves everything around so it just loops inside the function without actually creating a new stack for the next iteration. The iterative version here is very simple, but the recursive version is closer to the what again. Like this is actually very close to the definition of a factorial. This is what you do. So one of the big places recursion is compelling is when you can divide and conquer. In this case, we've got some readable but non-mutated variables, which is part of, sort of a functional methodology. And you end up with essentially a log n depth on the stack, making your approach to the 1,000 deep stack much less likely. In order for this quicksort to hit even 40 deep, you have to have 1 million items in it. So, like, just for fun, let's look at removing loops from our code. It's sometimes, probably most of the time, a bad idea for both readability and performance reasons, but it's really worth looking at to see how it might be useful in different ways. Starting with this first loop, this is the normal imperative sort of Pythonic way to do a thing. The map-based loop does the same thing, but it doesn't have the E for state. Map runs func for every instance inside it, which is exactly what for E init does. You can also do some kind of weird, like imperative style, like function slamming almost. Like this, do it for the functions. You can actually create an imperative-like structure where you're doing F1, F2, F3 on a piece of data, but instead you're actually running them like in one line, which is a little weird. It's not very Pythonic. Can be done. So as far as callables, like there's lots of callables in Python. Emphasis in functional programming is calling functions. This list is not exhaustive. There's a lot of other callables. But again, Python's multi-paradigm. We've got an emphasis on object orientation. And those classes, like the instances there that define the call method, all of those are meant as containers for the data. So, and that is opposite of this functional style, which emphasizes both immutability and pure functions. And accessing state isn't pure. Pretty much all of OOP is terrible in that it all has state. Like, that's the point. So the first one of these callables is obviously the easiest, named functions and lambdas. Like lambdas, not as easy, but like hopefully everybody's defined a function in Python. Hello1 and Hello2 are the two main ways of doing that with named functions and lambdas, and they do the same thing. They have different naming conventions inside. You can bind them, obviously, to other things. Make adjustments to the insides. But your the functions are good because they isolate your state and they avoid contamination of the enclosing namespace. So everything outside of Hello 1 wouldn't see variables that are inside Hello 1 unless you do things like use global and non-local. Those allow state to leak out. We don't want those. Data types can also be mutable inside functions. If you pass lists to functions, you can change them inside the function. Like, don't do that. Next is closures and callable instances. These are two very similar callables. The second is the closure. They seem to do the same thing, but the first one has a couple of subtle issues. As you can tell from the little code snippet on the right, the thing that's only supposed to add 5 can be changed. Like, you can reach in and touch the state and make it do something else. In this case, we change it to make it add 10 instead of add 5. That's sort of not good. Like, that's unintended, terrible side effects. You can use static methods of instances to avoid polluting either your global or your module namespace. In this case, we're literally just using these static methods to hide, essentially, these methods inside this class. Class doesn't have any state. We don't want it to have any state. And then generators. So in principle, a generator can be a pure function in that it has the same output for a certain input, but they generally have a great deal of internal state. It's at the boundaries of the call signature and the return value, so it sort of acts like a side effect-free black box, which is good, which is what we want if we're programming, functionally. But as you can tell, like we've got candidate, we've got found, we've got all of this state inside get primes. Let's see. So multiple dispatch is a way that a lot of different functional languages solve this. I've seen a couple of talks at the functional programming group where they pattern match, and that's what we're going to do. This is the start of a little bit of rock, paper, scissors. So the point is to create multiple functions with different call signatures to pattern match your arguments. We'll reduce explicitly conditional branching and use hopefully more intuitive pattern descriptions. So this is the sort of Pythonic, very imperative, very branchy version of rock, paper, scissors, where we can pass paper and rock to beats and figure out what beats what. That's the whole point of this. But we've got 16 different ifs. That's a little confusing. It's very error prone. Hopefully you don't miss one. Duck typing is a little better. That's very much more Pythonic. You pass things, and if it's meant to handle it, it will. That's sort of a very big thing in Python. But we haven't really reduced the amount of code. There's a reduction in complexity within each of the callables, and we've reduced the nested conditionals by 1, but it's pretty much the same size. This is more of a functional way of pattern matching, and this is a strange little module, multiple dispatch, and this is an example of a decorator, which we'll cover here in a bit. But we have to write out a lot of cases, but each one of the cases is very clear. the first one handles rock versus rock, and it returns none. Neither of those win. Rock, paper. Paper wins, so we return Y, etc. And basically, we've got the function down at the bottom that is handling all unknown cases. Like, we don't know what these things are. Or we don't know what either one of these is. Like in the beats rock versus 3. Somebody should expand this example to include Spock and Lizard. So in Haskell, you get this fun sort of lazy data structure. And this is actually Haskell code, so if you're terribly confused, this is not Python. But this is the same method, but it's lazily evaluated. The comprehension that's in this is actually where Python got its, I guess, inspiration for comprehensions. And another fun thing is that this is an infinite sequence, and you can jump into the middle of it, and Haskell will generate all of the intermediate values for you so that you get the right numbers. And we can emulate this in Python if we want with this fun little expanding sequence method, which basically caches what we don't have until we get to the point where we have what we need. It auto-expands to the necessary size. And as you can tell from the code on the right, it sort of sticks. Like, once you ask for the 100th prime or the 101st prime, like, suddenly primes is 101 long. But it only does it as you need it. So Itertools is a very useful method or package in Python. It's super powerful. Has very carefully designed functions for performing iterator algebra. And the basic goal of this module is to give you the building blocks to avoid performing computations before they're required. So you don't have the memory requirements, you don't have the potentially slow I/O until it's required, etc. All of these iterators are lazy sequences rather than realized collections. So when you combine them with functions and recipes and Itertools, they can keep that property. So you don't have to have all of that in memory. So your goal is to avoid performing computations before they're necessary. Before sucking up RAM before it's necessary. So basically, iterators are lazy. Itertools helps them keep that way or stay that way. And this is an example of what you can do with Itertools in that, so Fibonacci is a stateful class that keeps a running sum, with the A and the B, but instead we can create this sort of lazily evaluated iterator to generate both current number and the sum. And let's see, zip and accumulate T, yes. But these things don't require the method to realize its entire collection. So we don't care that it's 101 long or 1,000,000 long. It will eat as much as you want to eat. It's a buffet. So chaining iterables is kind of interesting. I personally haven't had a lot of reason to do anything quite like this, but counting to infinity 3 times, you can do that. You probably won't get past the first one. If you can, I want to see your code. and your computer. I want one. But for some large iterables, chaining these can be useful. This list of files in the second example can actually even be a lazy iterable. The huge.log and gigantic.log, you don't have to have an actual list for those. You can give those iterables. So your chain from iterable would be like multiply deep chaining. And so besides being able to chain with Itertools, there's a collections.chainMap, which works with dictionaries or any collections that follow the ABC mapping and are iterable. So it iterates over their keys. And just as we chain multiple sequence-like iterables, we can chain together mappings without having to create a larger concrete one. So again, we're avoiding that memory impact until we need to. And chain map is really handy, but doesn't alter the underlying mappings that you use to construct it. So getting into higher order functions. Again, it's a function that can take functions as arguments and or returns a function. And you can chain them and combine them like the functions in Itertools. So most functional languages use these three functions as their primitives. Sometimes they have other names, but like MapReduce, like everybody probably is familiar with that. If you've like written any internet-like things ever, maybe. Filter is also super useful. I think we're going to cover some of what they do, but almost as fundamental is this concept of currying, which gets its name from Haskell's curry. In Python, it's called functools.partial, and it's a function that takes another function and some arguments to pass that function, and then returns a function with fewer arguments. That made sense to everybody, right? Did it really? So essentially, let's see. No, we don't have a good example for that. Like let's say you have a function that you want to call a lot, but you always want the first argument to be 0. You can curry this and do a partial and say pass 0 for the first argument. And you'll get another function that does what the first function did, but always with a 0 for the first argument. There's not a lot of very Pythonic reasons to do that.
I use it like when making the logger. I might, if I'm trying to say a particular block of code, I might go ahead and apply to
You'll
my logger.
curry your log function so that
log function and set certain parameters to it, and then use it for the rest of it. And I've already set up certain parameters.
Right. Okay. So that makes sense. Toby's saying that he curries his log functions so that, like your source information as coming from that function is probably very typical, stays the same throughout that one function, and you can use probably a very much shorter name to call your log function instead of go to this other module .log . So that makes a lot of sense. So map, here's what map does. The comprehension version versus the pizza version, because it's here. Basically, map runs transformation on every item in iterator. Like that's its point. Filter does what you'd expect. If predicate is true, then it puts iterator, or the item from iterator, into filtered. And then reduce. Like sum is a good example of something that's reduce-like. Sum doesn't necessarily do exactly what reduce does, but it's essentially the same thing. And here we're using the operator .add, which is plus, to all of the items in it, and we're starting with 0. Like if we used operator.mul and started with 0, like we don't even have to call it. We know the answer is 0. Because
does a reduce function always have to return just one value? Because is that by definition what it has to do?
I think so.
It returns one value, but that value could be like class.
Right. That value could be
It could be a string.
could be a dict. It could be a tuple. It could be any you know.
You're not going to return like 2 strings.
Right. And obviously your function that you're calling reduce on would need to know how to deal with those things in order to return all the same things. So map and filter are really reduce. They're sort of special cases of it. Anything that, these examples are very awkward, but anything that you can compute from a sequence can be expressed from a reduction. Like obviously the map add 5 is much simpler than doing a reduction over a range. Same with the filter for is odd. Like you can do it either way. Filter is probably a lot easier to read. So this is like I actually had my colleague Josh write a compose function for me because I hadn't stumbled upon this wonderful document yet. And his was a terrible mess of lambdas. It worked, but it was terribly unreadable. Right. Yeah, that's Josh. But this is useful for when we want to, actually compose the output of multiple functions. And in this case, we're doing it with simple, like really ridiculously simple functions. Like we're multiplying by 2, subtracting 3, modding 6. In this example, like, write out the expression. Don't go full functional for that. It's horrible. And the all call down here at the bottom shows that they do the same thing. They all match. Like every one of those is true. But when you're getting to, when you're using functions that are more complex than these 3, where you've got logic and branching, like use the heck out of compose, especially if you're calling them multiple times on different things. It's one of those, it is a very functional style of writing programs in other languages and other more functional languages. But you really have to think about what you're doing in order to wrap your code and your head around writing it like that in Python sometimes. This operator module makes some of that easier, like the add 3. You can do that with the add module. That's sort of its point. Any of Python's prefix and infix operators have a named function in this operator module. So .add, .mul, .sub, I think it is. It might be subtract. And these names look a lot better than those weird lambdas that we were using in the previous slide. So there's actually surprisingly few higher order functions in Itertools. The numbers increase very slowly because the core Python devs are very resistant to going full functional. And I really don't blame them. But these are the things that are really core to the Itertools module. And it's really easy to forget that one of the most common uses of higher order functions is as decorators. This is syntax sugar that takes a function as an argument and gives you an enhanced version. Like, there's no enhancement going on. Well, I don't know. We don't know. Enhanced, we don't know what it does, but it enhances it. Obviously. Like, it's Iron Man. But these two methods are essentially the same in that we're wrapping the function with the enhancement in both methodologies. So decorators have a lot of uses. This first one marks a function as an asynchronous coroutine. Like, I'm not even going to get into like all of the async IO stuff. Like, that's a whole different talk. The next memoizes a function, the LRU cache. So you can wrap a function in this as long as it's pure. Like, you don't probably want to memoize a function whose output will change based on things other than what you're passing, because if you do, like, you will cache the first value for that particular set of arguments. And that's what that does is, let's say you're going to add a whole bunch of small numbers. You might actually get a performance benefit from wrapping operator.add in LRU cache. I could doubt it, but it's possible. Maybe if they're really big numbers and you're doing the same big numbers over and over again. But essentially, every time you call one of these cached methods, it will look up the arguments and say, did I call this before? Yes? Oh, well, this is the answer that I got, and it will return from there, instead of having to recompute everything in your method. The total ordering makes it easier to write custom classes that want to use inequality operators. So, like, if you want to compare two rocks from our classes earlier, and they have different attributes, total ordering helps make them order the same way. It helps them, retain that. And then this last one, functools wraps, makes it easier to write decorators. It does a lot of interesting things in Python. It changes the name of your wrapped function to let you know that it's wrapped. Does a couple other things. Super fun and interesting to sort of toy with, especially when you're wrapping functions with decorators and like you have a hard time telling what it is you wrapped at some point when you're debugging your code later because it wasn't as functional as you thought. But that's what I've got for you today. So, do you guys have any crazy functional programming questions? Because I probably can't answer them all, but I can help, maybe. Get you in the right direction, at least. No? Perfect.